Good afternoon. My name is Ludger Wifus Bailey, and I'm from the Religious Studies Department. And it's my distinct privilege and pleasure to welcome you all on behalf of the Terry Lecture Committee, to the second installment of this year's Dwight H. Terry Lectureship titled Cosmic Society, the New Universe, and the Human Future. In these presentations, our distinguished guests, Nancy Allen Abrams and Joel R. Primack, will present the emerging scientific understanding of the universe and our place in it. No one, and perhaps even no couple, could better answer to Dwight H. Terry's charge that the lectures explore how scientific knowledge and philosophical insight inform religion and religion's application to human welfare. They have co-authored articles on quantum cosmology and Kabbalah, as well as numerous articles on science, policy, space policy, and the cultural implications of modern cosmology. Nancy Allen Abrams is an attorney and philosopher of science who, in addition to her prominent work on the intersection of science and politics, engages the question of how to place the discoveries of modern cosmology into a cultural context. And she's also a composer and musician, and several of her musical compositions will accompany videos shown in the Terry Lectures. And today it will be the music to the last video. A professor of physics at University of California, Santa Cruz, Joel R. Primack, is one of the creators of the modern picture of the universe. He contributed to what we call the standard model of particle physics and is one of the principal originators and developers of the theory of cold dark matter. As a specialist in the formation of and evolution of galaxies and the nature of dark matter, Professor Primack's current research uses supercomputers to simulate and visualize the evolution of the universe under various assumptions. Together, you co-authored the book The View from the Center of the Universe, Discovering Our Extraordinary Place in the Cosmos, and you co-taught a popular course called Cosmology and Culture at the University of California, Santa Cruz for more than a decade. And given your opening lecture yesterday, I have no doubts as to why this course was so popular. You dare to ask large-scale questions, and you call on us to develop a vision of the cosmos that allows us to confront humanity's pressing global problems. In all of this, you remind us that our role as scholars in universities can be not only to produce true statements about the universe, but also to shine light onto our humanity in a world that is at once interconnected, open for analysis, and profoundly beautiful. Let us now listen to the second lecture entitled Stardust plus Time equals Us. Thank you, Nancy, and thank you, Joel.
Thanks very much for that wonderful introduction, and thanks to the audience for your attention. And if anyone has a cell phone that hasn't been turned off, please turn them off now.
What are we human beings made of? Literally. Are we made of flesh and blood, sugar and spice and everything nice? To become a cosmic society, we need to appreciate at a much deeper level what we are and how we fit into the universe. We humans are made of a rainbow of atoms that were cooked up inside ancient stars or formed during supernovas and spewed out to travel through space for billions of years to evolve into our planet and us. We humans are 90% stardust by weight and 10% hydrogen, which is mostly in our H2O. We and the ground we walk on are literally made of stardust. Well into the 20th century, scientists believed that everything is made of atoms, and everything on Earth actually is. But Earth is extremely atypical of the universe, and the way things are put together here is not a good basis for extrapolation. Let's come back to the cosmic Ouroboros that we introduced yesterday in the first lecture. As we showed then, on vast size scales, the laws of physics that control events are not the same as in daily life on Earth or on atomic scales. Size makes all the difference. So we may be made of atoms, but what's the rest of the universe made of? Without knowing that, we can't possibly imagine how we fit in. The theory that answers this question is the double dark theory that we discussed yesterday. It tells us that the two dominant ingredients in the cosmic recipe are dark matter and dark energy, both unearthly things whose nature is still not well understood. We stardust beings are the beneficiaries of dark matter and dark energy because their interaction over billions of years has shaped the universe. The other crucial ingredient in this equation is time. And in this lecture, we'll explain first what the ingredients of the universe are, and second, how to think about cosmic time. We explained in Lecture 1 that we humans are close to the midpoint of all possible sizes. In this lecture, we'll explain that we're made of the rarest material in the universe, stardust, and that we are at the center of the visible universe. Gradually, as we integrate these characteristics in our minds, we begin to understand how we fit into a universe that at first defies intuition. This is what the universe looks like to the Hubble Space Telescope. It's very beautiful, but it's extremely misleading because all it shows is light, and all light can reveal is half of 1% of what's actually out there. The other 99.5% of the universe is invisible. We call this symbol the pyramid of all visible matter, and of course, we have borrowed it from the pyramid on the back of the dollar bill. We're using it here, though, to represent everything that we can see in the universe with all our instruments. The volume of each section of the pyramid is proportional to the amount of that ingredient in the visible universe. The ribbon at the bottom says in Latin, the new order of the ages, and that's what this new universe picture is going to become.
Almost all the atoms in the universe are just the two lightest kinds, hydrogen and helium. That's what comes out of the Big Bang in roughly the proportion by mass, 3 parts hydrogen to 1 part helium. They fill the entire bottom section of the pyramid. The hydrogen and helium became stars, and inside those stars, nuclear processes created new kinds of atoms like carbon, oxygen, iron, and all the other heavy elements. These heavy elements are ejected by dying stars, and they become stardust, floating through interstellar space. You see up on the left the periodic table of the elements. Hydrogen and helium are what the stars are mostly made of, and all these other elements are the stardust. The iron atoms in our blood, carrying oxygen at this very moment to our cells, came largely from exploding white dwarf stars. That's, on the right, the remnant of one of those explosions. While the oxygen itself came mainly from massive stars exploding as supernovas. These are examples of the remnants of supernova explosions. Most of the carbon and the carbon dioxide we exhale on every breath came from planetary nebulas, the death clouds of middle-sized stars like the Sun. It takes a star millions or billions of years to produce a comparatively tiny number of heavy atoms, and these bits of stardust then drift across time and space to come together to incarnate us. The Cat's Eye Nebula in the lower left is a particularly pretty example of a planetary nebula. Let's look at it first on a larger scale and then zoom in to the cat's eye. So that's a large-scale image, and that is the cat's eye. Let's zoom in. All that's left of the star ultimately is a white dwarf at the center. All the rest of the star is blown off in these colorful clouds of stardust that surround the star. On any planet in the galaxy or any other galaxy, wherever you find watery seas and land, there will be sandy beaches. This is because oxygen and silicon are two of the most abundant heavy atoms produced before a star explodes in a supernova. Free-floating in space, they combine with the hydrogen that's everywhere, making H2O and SiO2, water and sand, that travel together and become incorporated into new worlds. The capstone of the pyramid, the floating part at the top, represents the mass of the stardust compared to that of hydrogen and helium. It's about 2% of the total. The eye in the capstone represents the minuscule amount of stardust in us, that is, in all intelligent creatures. And it's the only cosmic ingredient not drawn to scale, since if it were drawn to scale, it would be a microscopic point. This pyramid represents everything visible in the universe. But what's all the rest? The other 99.5%. We call this symbol the cosmic density pyramid because it contains everything that gives the universe density, including not only matter but energy. As you can see, the pyramid of all visible matter is just the tip of a huge underground pyramid. The visible atoms are just half of 1%. The invisible atoms add up to an additional roughly 4%. It turns out there are 5 different ways that we can measure the total atomic content of the universe, and they all agree. So we're quite sure that we have this accounting right. The vast majority of the cosmic density is invisible stuff, dark matter and dark energy making up about 95%. Most of the matter holding our own galaxy and other galaxies together is cold, dark matter. Except gravitationally, dark matter hardly interacts with anything, including itself. So it can never make anything complex. It just makes big halos, as we call them, which are blobs of dark matter that surround and permeate each and every galaxy. Dark matter neither emits light as stars do, nor reflects it as gas clouds do, nor absorbs it as dust does. It also doesn't emit or absorb X-rays, radio waves, or any other form of radiation that astronomers have detected. We know it's there only because of its immense gravitation. Dark matter is not a good name, in fact, since the stuff isn't dark, it's invisible. It's transparent. But whatever it's called, it controls the origin and evolution of galaxies, galaxy clusters, and superclusters of galaxies. The largest portion of the pyramid, 70% or so of the density of the universe, is dark energy. This is the most powerful ingredient in the universe. And yet until 1998, we weren't even sure it exists, although it was a hypothetical possibility that I and other astrophysicists studied. Dark energy is connected to the expansion of the universe. Before I explain it, I'm going to take a step back and explain first what it means that the universe is expanding. All distant galaxies are being carried away from our Milky Way galaxy by expanding space itself. Imagine that we live in Galaxy A. We see Galaxy B moving away from us with a certain speed. Galaxy C, twice as far away, moving twice as fast. The arrow is twice as long. Galaxy D, 3 times as far away, moving 3 times as fast. But now let's look at the situation from the viewpoint of Galaxy B. Galaxy B sees our Galaxy A moving away at a certain speed, and the galaxy on the other side, equally far away, moving with the same speed in the opposite direction. And then Galaxy D, twice as far as Galaxy C, moving twice as fast, and so on. So the situation looks the same from every galaxy. Every observer sees exactly the same pattern in the motion of distant galaxies. That's how a uniformly expanding universe works. Of course, this picture just shows one dimension. Here's a 2-dimensional picture, with time increasing upward. Notice that the galaxies aren't expanding, just the distances between them. Most astronomers assume that the expansion of the universe was gradually slowing down because of the mutual attraction of everything in it. But in 1998, the amazing discovery was made that the expansion of the universe is not slowing down at all, but accelerating. Dark energy seems to be a property of space that makes space repel itself. The more space there is, and of course increasing amounts of space are inevitable in an expanding universe, the more repulsion, The more repulsion, the faster space expands. The faster it expands, the more space, the more repulsion. This leads to an exponentially increasing expansion, which may go on forever. Until only about 10 years ago, astronomy students were usually taught that there are 3 possible futures for the universe. 1, it can expand forever at a constant rate. 2, it can slow down forever asymptotically. That is, the rate of expansion would get closer and closer to 0 without ever reaching it. That's shown by this curve getting, the slope getting lower and lower. Or 3, if there's enough matter in the universe, the gravitation of all that matter would eventually slow the expansion to a halt, and the universe would begin to contract. So it halts there, and then it starts to contract. In the figure, all the curves cross at the point labeled now. It's been set up that way, when the universe is a size, the size it is now, represented by 1. The third possibility led people to speculate about whether there would be a big crunch as everything came back together again, and if so, whether there could be another Big Bang, ad infinitum. I bring this all up because all these alternatives have been talked about so widely, and you should understand that we now know they're all wrong, which reflects the rather primitive state of cosmology until recently. Now we have convincing evidence that the expansion of the universe is actually accelerating. So it's that red picture. What's happening is that the universe first slows down and then starts speeding up. The test of a theory, so how certain are we scientists that this whole kooky-sounding double dark theory is right? The test of a theory is not how logical, beautiful, or, on the other hand, weird or unlikely it sounds. The test is how accurate are its predictions. The double dark theory has predicted the observations successfully for more than 20 years, and as huge amounts of new data have become available, more recently from the wonderful telescopes on the ground, like the Keck Observatory in Hawaii, and in space, like Hubble Space Telescope, the predictions have continued to be right. Crucial evidence has also come from satellites observing not light, but the heat radiation of the Big Bang. I'll show you some of the evidence that has convinced astronomers all over the world. Now, what's plotted here, it's called power, is basically the frequency of spots of a given size. This is the sphere surrounding us of the cosmic background radiation, the heat radiation of the Big Bang. And the different colors correspond to very slight differences in temperature in different directions, differences of a few millionths of a degree. The large scales, many degrees, were studied by the COBE satellite, whose results first became available in 1992 rather. Starting in 2003, the Wilkinson Microwave Anisotropy Probe, a NASA satellite like COBE, started to release its data, and the most recent data release in 2008 is represented by the white dots on this diagram. What this shows is that 1 degree size patches are particularly favored. Half degree is disfavored, third of a degree is favored, quarter degree is disfavored, and so on. Now, the important thing is to realize that this curve, the prediction of the double dark theory, was calculated before any of this data became available. And the fact that every single point lies where it was predicted to, also in these ground-based experiments that probe smaller scales, is a triumph for the theory. We now have a new satellite, the Planck satellite, that will soon start reporting its data, and it will cover this region with greater precision. And it'll be interesting to see if it continues to agree with the predictions. I think most astrophysicists expect that it will. I certainly do. So what this shows is that the double dark theory correctly predicted the properties of the heat radiation of the Big Bang, the cosmic background radiation. But the same theory also correctly predicted the distribution of matter on all size scales that astronomers can study, from smaller than galaxies to clusters of galaxies to superclusters of galaxies, all the way out to the cosmic horizon. That's why we take the double dark theory so seriously. I could show you a great deal more evidence. What happened, according to the double dark theory, is that in the early stages of the universe, there was relatively little dark energy because there was relatively little space. The universe hadn't had time to expand very much. However, there was the same amount of dark matter then as now. For the first 9 billion years or so, the gravitational attraction of the dark matter did in fact slow the rate of expansion. But the expansion was still going on, producing more space, and so the dark matter thinned out. But dark energy apparently doesn't thin out, perhaps because it's a property of space itself. Its relative importance thus increases. Now the repulsive effect of the dark energy has surpassed the gravitational attraction of the dark matter as the dominant effect in the universe on large scales. The turning point was about 5 billion years ago, coincidentally, just about when our solar system was forming.
Now let me just give you a simpler way of thinking about this. Imagine that the entire universe is an ocean filled with dark energy. And on that ocean, there sail billions of ghostly ships made out of dark matter. At the tips of only the tallest masts of the largest ships are little tiny beacons of light. And those beacons of light are what we call galaxies. With Hubble Space Telescope, we can only see the beacons. We can't see the ships and we can't see the ocean, but we know they're there through theory, specifically the double dark theory that Joel's been talking about. Now, this oceanic imagery has a certain resonance with ancient Egyptian and biblical cosmologies because both of them also envisioned that the primeval water, an unearthly substance, not normal water, predated the creation and continued to surround the world. The creation was in the middle. The world was created in the midst of this primeval water. But here's the twist in our modern version. Dark matter is indeed primeval, and it came out of the Big Bang, and it does surround our galaxy. But dark energy is creating more of itself all the time, and the larger the universe expands, the more dark energy there is and the faster it's being created. Now, we could leave it here. We could just say, oh, how interesting. But if we take dark energy seriously, it means we have to begin thinking in a new way about what we normally call outer space. Most people use the phrase outer space to mean anything outside Earth's atmosphere. But this communicates a very static picture of the universe. It's left out the whole idea of expansion. If we think of outer space as starting outside Earth's atmosphere, then we need to think of it as stopping at the edge of our local group of galaxies. Now, galaxies are often bound together by gravity in clumps, and big clumps are called galaxy clusters, and little clumps are called groups, galaxy groups. Our Milky Way is part of a small group called the local group, which includes 2 big galaxies, Milky Way and Andromeda, plus a lot of smaller galaxies. Our local group is bound together by gravity, so it doesn't expand anymore. It travels as a unit in the universal expansion. Yes, so the husband says to the wife, don't feel bad, Loretta, the entire universe is expanding. Well, you know, it's a great excuse, but it's wrong, because there is no expansion on Earth or inside our entire galaxy. Outside the local group, though, the universe is expanding faster and faster. Gravitationally bound groups, though, like our local group, are not expanding, they're contracting. And as the gravity of the galaxies continues, it makes them fall together, and they will eventually merge. And so, all the space inside our entire galaxy and between our galaxy and the other members of the local group is a special kind of space because it's been tamed by gravity. Outside our local group lies the real outer space, wild space. On a huge scale, dark energy is tearing apart all large structures and accelerating the rate of expansion. Wild space is carrying hundreds of billions of galaxies away from our local group in all directions. So here's this guy that's drunk. He's sitting on the stoop and he says to his friends, it's a little hard to read, quarks, neutrinos, mesons, all those damn particles you can't see, that's what drove me to drink. But now I can see them. And there's Great truth to this, because now we too can see what cannot be seen. To show you how wild and tame space work, we have to visualize the invisible. But we're going to do this not with the help of alcohol, but with computer simulations.
So I'm going to show a video of a dark matter simulation that illustrates what Nancy's just been talking about. The simulation shows a small part of the universe. Initially, you'll see it expanding, but soon the screen is filled with a region that's become bound together by gravity, and it stops expanding. So watch the video and see if you can tell when it stops expanding. Let's look at a few stills. So there, about 49 million years after the Big Bang, it's just starting to expand in this video. Here, about 374 million years, it's expanding very rapidly. By about 2.2 gigayears, that's billions of years, the central region has actually stopped expanding, and this material is flowing toward it. Here's that same central region, now about 6.7 billion years after the Big Bang, about 7 billion years ago. And the central region has pretty much stopped expanding, but this piece is still sliding away. If we look somewhat later, now 9.5 billion years after the Big Bang, that piece has almost completely left this field of view. This region has gotten a little bit bigger, but that's not because it's expanded, it's because material is flowing into this region. And then if we look today, that's that same one we were just looking at, about 9.5 billion years, and this is today, 13.7 billion years. This is tame space. This is wild space. It's still expanding. So this is to illustrate wild and tame space. Let's look again at that video, and this time try to imagine what's the tame space and what's the wild space as the video goes on. So in these dark matter simulation visualizations, what looks bright is in reality completely invisible. We're just looking at dark matter. The video uses brightness to represent the density of the dark matter. The brighter a region appears, the more dark matter it contains. Now, I'm going to show you a more elaborate simulation. In these videos, we're going to look at the evolution of a region about 100 million light years across, from soon after the Big Bang until the present. But if we tried to show the expansion, you wouldn't be able to see what was happening until the region grew into nearly its present size. You can't see what's going on here or here. So on the bottom, we expand all of these up to full size. And when we do that, we're showing the evolution of structure, but not the expansion. We astronomers call this working in co-moving coordinates. We will also rotate the volume in the video that I'm about to show slowly to help show the 3 dimensions. There's a clock in the lower left corner showing the number of billions of years ago. Now, you'll notice that the dark matter starts very smooth, but just a couple billion years after the beginning, a tremendous amount of structure has formed that just becomes more distinct and starts to split up as time goes on. It turns out that what's happening is matter is being attracted to what we might call wrinkles in space that are laid down by processes that occur in the earliest moments of the universe, a period that we call cosmic inflation. We're going to come back to that in the next lecture and also in the last lecture. But here's the simulation. So already, just a billion years after the Big Bang, you can see a lot of structure. You can see these filaments of dark matter starting to form. The bright yellow places mark where galaxies are forming. Remember, you're only seeing invisible dark matter. The computer is making it visible to us. But notice that where these filaments cross, you get a large number of these bright spots where lots of galaxies are forming. And those are the superclusters, and at their centers, the clusters of galaxies. Our galaxy doesn't lie in a cluster, it just lies in a small group along one of these filaments. You just saw how the cosmic web of dark matter forms, and that at the intersections of the filaments, the density is much greater. That's where clusters of galaxies form. Now we're going to look at a video that my colleagues and I just finished about 2 weeks ago. Earlier this year, we ran what is, I think, a path-breaking simulation. We call it the Bolshoi simulation because when my Russian collaborator, Anatoly Klipin, suggested that name, we all burst out laughing. Bolshoi is thought by many Americans to mean ballet or a particular ballet troupe. Actually, in Russian, it just means big. The Bolshoi Theater is the big theater in Moscow, and it's where the famous Russian ballet troupe often performs. And this is the highest resolution, big simulation of the evolution of the double dark universe that has yet been performed. In this simulation, every dark matter halo that could host a visible galaxy is shown. First, I'm going to just look at a bunch of still pictures and zoom in to see some of the small structure. Now, we're going to fly through a region of the simulation about 100 million light years across, surrounding a dark matter halo hosting a large cluster of galaxies. There's the region hosting the cluster. Now the camera's moving in, but still rotating around. We're in the process of analyzing the simulation outputs. Statistical tests are showing that the distribution of dark matter halos in this and similar simulations looks exactly like the actual distribution, both nearby and far away in the universe. Now I want to show you a magnificent simulation called the Aquarius simulation by a European group led by Volker Springel. It simulates the formation of a Milky Way size dark matter halo, which is 10 times smaller across than the region I just showed you. In these sorts of simulations, a lot happens much earlier. Because this relatively small region stops expanding fairly soon, we can show the expansion in this video. In fact, the camera moves slowly closer to the central dark matter halo. Again, we're rotating the image to show the three-dimensional structures. This is the time. We're starting at about 80 million years after the Big Bang. Now, 120 million years, 0.12 billion years. This is the redshift, for astronomers who are familiar with that. This whole region is going to collapse to form the dark matter halo of a Milky Way-sized galaxy. So it starts out very filamentary, but you'll see that the filaments are steadily getting thicker and drawing together. It's fun to follow individual dark matter halos, and what you'll see is that they flow through the dense regions and then out the other side. But they lose some of their particles, some of their mass every time they do that. Dark matter lumps can go right through each other. As the camera moves in, this region, representing 500 kiloparsecs, that's comparable in size to the dark matter halo of our galaxy. That's getting larger because we're moving slowly closer to the center. Now, this is an object that will host a fairly large galaxy. Some of these are going to be swallowed by the forming Milky Way, and their stars will just become part of the stars of our Milky Way galaxy. Something like 10% of the stars in the Milky Way did not form in the Milky Way. And others are going to be satellite galaxies of the Milky Way. More and more of these satellite galaxies are being discovered with more powerful telescopes and better search techniques. So, how big is our galaxy, the visible part of the galaxy? That's how big. It's pretty small. That's 100,000 light years across. This is about 1.6 million light years across, that 500 kiloparsecs. This is what we call the relaxed or virialized region of our Milky Way-sized halo. And this part is bound to it, but it hasn't relaxed yet gravitationally. So there you see how tiny the visible galaxy is compared to the dark matter halos.
We've introduced the symbols of the cosmic Ouroboros, which represents all possible sizes in the universe, and the cosmic density pyramid, which represents all the ingredients in the universe. And both capture aspects of the real universe that are hard to visualize, but neither of them represents the crucial aspect that animates the universe, time. Now, we're going to switch back from computer simulations of invisible dark matter to actual Hubble Space Telescope photos. We've used this photo before. It's the Hubble Ultra Deep Field. You can't see time in this still photo either, but by using the measured and the estimated redshifts of these galaxies, to determine how far away they are, the computer lets us spread them out in time and zoom into the picture. Redshift is a measure of how much the light coming from distant galaxies has been stretched by the expansion of the universe. Since the farther away a galaxy is, the faster it's expanding away, the redshift tells us its distance.
As in the voyage we took to the Virgo cluster in the first lecture, we're going to start out looking toward the constellation Orion. But this time we're going to focus in on a region below and to the right of it. In the first part of this video, we will zoom in toward regions that Hubble Space Telescope has surveyed. We're now going to focus on a very dim, faint region that Space Telescope stared into for more than 2 full weeks in order to gather enough light to see the faintest and most distant galaxies. First, we see the galaxies as if we're looking at a photo in 2 dimensions. And notice, some of them look very odd indeed, not at all like the nearby spiral and elliptical galaxies. Now let's zoom in. First, the nearby galaxies go sliding off to the edge of the field. The nearby galaxies, especially the big ones, are disk galaxies like the Milky Way or elliptical galaxies. Light from the ones just disappearing now has been traveling toward us for about 5 billion years, before the Sun and Earth formed. Now about 8 billion years. But as we zoom deeper in, the nature of the galaxies changes. We're no longer seeing big galaxies like those near us now. The earliest galaxies, those that formed in the first 2 billion years after the Big Bang, are small and irregularly shaped, but very bright because they're forming stars rapidly. We think they're ragged looking because at these early times the universe was a lot smaller than it is now, and the dark matter of a forming galaxy was frequently colliding with the dark matter of other galaxies in this early bumper car era. The Hubble Ultra Deep Field showed the galaxies in just a little pinpoint of the sky. Now I want to show you the large-scale distribution of galaxies as mapped by the ongoing Sloan Digital Sky Survey. So this is the picture that we looked at the last lecture, where we had this trip across the local supercluster to the Virgo cluster. The local supercluster, in turn, is just a little tiny region at the bottom of this big V. This shows some of the large-scale structure that's been mapped by the Sloan Digital Sky Survey. The Sloan Digital Sky Survey has mapped all of the reasonably bright galaxies in certain directions that they're mapping them in, out to about 2 billion light years. The really bright red galaxies, shown here in red, out to about 6 billion light years, their distance today, and the quasars out to a distance today of about 28 billion light years. Let's look at how these galaxies are distributed in space. So we're backing rapidly away from our region of the universe. We're about 1 billion light years out. As these first luminous red galaxies come in, we're about 2 billion light years out. The galaxies are all piling up in front of each other in this central region, but off on the side you can see that there are walls of galaxies surrounding regions with hardly any galaxies at all, cosmic voids we call them. To get the three-dimensional image of how these galaxies are distributed, though, we have to rotate this visualization. And what you see is that the mapped sections look like slices through a sponge. Walls of galaxies surrounding cosmic voids. Now the quasars in blue. And now the cosmic background radiation, where the colors represent slight differences in temperature. we're looking at the entire visible universe from the outside, something that can only be done with the help of a computer visualization.
This video ends by showing the sphere of the cosmic background radiation from the outside, as though we are outside there and not part of the universe, not inside the sphere. To the extent that this is a helpful stance for scientists who are gathering data, this imagined standpoint does serve its purpose, but for the rest of us, it's extremely misleading about reality. We modern people, both scientists and non-scientists, who lack the intuitive sense of belonging to the universe that people had in ancient times, we need to start visualizing our universe from the inside, where we actually are. Otherwise, we will always misinterpret ourselves, feeling as though we're outside, sensing a familiar existential isolation, and looking at a universe in which we play no part. So let's introduce a new and more accurate standpoint. Joel and I call this symbol the cosmic spheres of time. These concentric spheres don't represent just space. Each sphere moving outward represents an earlier and earlier time in the history of the universe, with our galaxy as it is today at the center, and the earliest time, the Big Bang, represented by the outermost sphere. When we look out into space, we look back in time. Why is that? We see when light hits our eyes carrying a picture of its source. Light travels through space at a fixed speed of 186,000 miles per second. It's very fast, but it's finite. When we look through telescopes, we see galaxies as they were eons ago, when the light that's reaching our eyes now left them. The farther away a galaxy is, the longer its light has been traveling to get to us, and therefore we see it at an earlier stage in the evolution of the universe than we see the galaxies nearby us. So we are looking back in time when we look at them. We are at the center of our past. The past is not over. It's racing away from us at the speed of light, like ripples from a pebble thrown into a pond, but not in circles, in spheres, spheres of time.
The era when our sun and earth were forming 4.5 billion years ago is still out there, spherically surrounding our solar system, our galaxy, and all the nearby superclusters. Far beyond that is the era when the first big galaxies formed. These images are taken from the Hubble Ultra Deep Field, and of course they're much larger than the scale of this figure. But what you'll see is that most of these galaxies look pretty much like the nearby galaxies, except as you get out close to the sphere where the big galaxies are starting to form. But then, this next sphere represents where bright galaxies first started forming in the first billion years of the universe or so. And these are all pictures of those odd galaxies that you saw in the ultra-deep field that don't look anything like the nearby galaxies. Beyond that is a region that theory tells us is the cosmic dark ages, the period before bright galaxies had formed. Earlier still lies the sphere of the cosmic background radiation, and at last, the cosmic horizon, the Big Bang. With telescopes, we see galaxies as they were millions and billions of years ago, but in the cosmic spheres of time, we're showing you what they looked like then, but placing them where they are now. Because of the finite speed of light, we can't know what they look like now, but we can calculate where they are now with theory. Once again, the double dark theory.
No scientific explanation that treats us as objective observers of the universe out there can ever be satisfying. And what's more, no such explanation can ever be accurate, because the universe exists on all size scales, and on our scale, we're indisputably here, and we need to be explained. The cosmic spheres of time place us at the center, but it's still drawn as if they're up there on the screen, and here we all are out here looking at it. So jump into this picture. In your imagination, take your place there, at the center of the symbol, at today, and then close the spheres around yourself. We are physically immersed in the past of the universe. Take a moment to absorb that. Our place in the universe is not a geographical place, but a meaningful place created by the interaction of space, time, light, and consciousness. Without consciousness, after all, there would be no visible universe. The cosmic spheres of time are real because the past is real. We know that because evidence of it in the form of light is arriving constantly. Let me illustrate this again with an image. In the ancient world, when people needed to get a message somewhere, they had no instant media, so they had to send a runner, and that took time. So imagine that a runner were just arriving here today from ancient Greece, breathless, with the news that the Persians had just been defeated at Marathon, and we were the first to hear it from his lips. Messengers in every form of radiation, and speaking the strangest languages anyone has ever heard, have been running for billions of years toward the Earth and are arriving at our telescopes at every moment from all over the universe with news of their eras, their ancient eras, and our generation is the first to hear them. The cosmological revolution of today is human beings beginning to decode all their languages, understand the news, and pull the whole story together.
It's everyone's story. It took billions of years for galaxies to form, for stars to form inside the galaxies, for stardust to become common enough so that rocky planets could evolve. And then, on at least one of those rocky planets, for life to evolve to the complexity of beings like us, who can reflect on it all. Many billions of years were required for the evolution of intelligence. Stars continue to form, and some will be burning for trillions of years. There's no reason life could not go on that long. If the dark energy keeps on accelerating the expansion of space, all these distant galaxies will eventually disappear, and our own local group of galaxies will become, for our very distant descendants, the entire visible universe. The overwhelmingly rich sky that we see in this photograph, dense with galaxies, will be known to our distant descendants only historically. The astronomical observations and understandings that we pass on will be an irreplaceable part of our heritage. And yet there are millions of people in the United States today who believe that the world was created 6,000 years ago as is, and that human beings have been on it the entire time except for the first 5 days. There are millions of people who believe that the end is near, that the rapture is coming. But we have a new story now. We humans were not here at the beginning, and we're nowhere near the end. We live in the middle of time, and in Lecture 3, we'll explore this discovery and its practical implications.
We, with the other potential members of the Cosmic Club of Intelligent Life, are at the peak of the cosmic density pyramid. An enormous base of material and phenomena in the universe support our existence, and over time have made it possible. Within the capstone that represents stardust, the fraction that's associated just with living things is extremely tiny. And within that extremely tiny fraction, the matter associated specifically with intelligent life anywhere in the universe is vanishingly small. And yet, it's only that which looks at and grasps this pyramid and the way that time has constructed it. It may even just be our eyes. We may be the only ones. The very human-looking eye in the capstone suggests mind or vision, unquantifiable things that transcend the issue of quantity. The eye reminds us that intelligence bursts out only from tiny bits of stardust. Intelligent life is the rarest and most complex phenomenon we know of in the entire universe. To become a cosmic society, as we've said in the beginning of this talk, We need to understand what we are and how we fit into the universe, but we also need it to matter again. The challenge is to know in our bones that we are connected to the universe that the evidence says exists. So now, imagine that you have suddenly lost your memory. You look at yourself in a mirror, but there's only this moment. You're unaware of any past, even the very moment before this one. You're solid, your cells are real, your heart is pumping, but how you got to the spot on which you stand, you have no idea. Who are you? There's no answer. You're not your family background, your personal history, the work you've done, your hopes for the future. These don't exist. You have no family, no associations. You're like a computer with hormones. You've lost your soul. You're listening to the latest music, buying the latest improved products, and believing the latest media interpretation of the world outside your room. This is all you know. Now instead, imagine yourself as a budding leaf at the very tip of a long branch of an enormous tree of time. And send your consciousness back through your stem and branches at lightning speed, down past your parents and grandparents, down the countless generations before them, through your ancestors roaming from continent to continent, your primate ancestors, down through all the animals that preceded them, back through the earliest life into a single cell, down into the complex chemicals that made it possible, down into the molten planet and the forming solar system, the birth of your carbon and oxygen and iron in exploding stars far across the galaxy, back to the universal expansion, to the creation of your elementary particles in the Big Bang. This is not fantasy. This is science. You are all this. Who you are is the sum total of your history, and how far back you take that history, how much of your own identity you claim, is up to you. We have an extraordinary and meaningful place in the universe, but only if it has a place in us. We hope to see you again next Tuesday for Lecture 3, This Cosmically Pivotal Moment. Thank you very much.